In 18.4, we start to introduce the idea of Gibbs energy. So I'll write that up here. So Gibbs was the physicist that was working on this idea a long time ago. And we know that the second law of thermodynamics says that delta S of the universe is greater than or equal to 0 for processes that are spontaneous. Of course, we can talk about and describe a process which is non-spontaneous, but for those that actually occur in nature, then the second law of thermodynamics holds. Well, what is the delta S of the universe equal to? So delta S of the universe is delta S of the system plus delta S of the surroundings. And so the delta S of the system plus the delta S of the surroundings must also be greater than or equal to 0. And the delta S of the surroundings can be related also to thermodynamic variables of the system. We know that the delta S of the surroundings is the delta H of the system, is the negative of the delta H of the system divided by T. So that is greater than or equal to 0. Okay, so let's do one final thing. Let's get this T out of the denominator. We can multiply both sides by T, and of course on the right side multiplying by 0 does nothing. On the left side, if we multiply by negative T, then we'll get just a delta H for the system, and we'll have a negative T delta S for the system. And then I lied a little bit. I said multiplying by negative T was not going to affect anything over here, but it is going to change our greater than or equal to sign to a less than or equal to sign. And this is now a very important equation. So for spontaneous processes, delta H minus T delta S is less than or equal to 0. And we can go ahead and put this in standard states just so that we can use this equation with our tables of tabulated standard thermodynamic values. And so we'll say that delta H naught minus T delta S naught is less than or equal to 0 for spontaneous processes. Well, this is great. We can take a reaction and figure out whether it's going to be spontaneous or not. And note that temperature is in there, and so some processes are spontaneous at some temperatures and not at others. But we can actually take this equation a little bit farther, and we can say, well, this quantity here, it's obviously very important. Let's give it its own name. And that will be the Gibbs energy of the reaction. So delta G naught is equal to delta H naught minus T delta S naught. And so based on the origins of this equation, we know that, actually let me just rewrite it out here. Delta G naught is equal to delta H naught minus T delta S naught. That's the way it's usually written. Okay. And if delta G naught is less than 0, then that means our process is spontaneous. Those are processes which occur in nature. If delta G naught is equal to 0, then we're in equilibrium. We can expect the state to remain steady. Concentrations and things won't change. Overall, there won't be any reaction taking place. And then if delta G naught is greater than 0, then that means our process is non-spontaneous. A non-spontaneous process. Okay, and in principle, a non-spontaneous process, that may mean that the reaction will go backward. We'll explore that idea a little bit later as well. Now we've defined this quantity Gibbs energy in terms of our other more familiar thermodynamic functions, and it's been given this meaning in relation to spontaneity. So if the delta G naught is negative, then the process is spontaneous. If it's positive, it's non-spontaneous. And delta G naught equaling 0 is that perfect middle ground where you're at equilibrium. And I want to point out that we can sort of change the delta G of a particular system by changing the temperature or by changing the concentrations. Right here we have an equation that relates to standard concentrations. That's 1 atmosphere of pressure for all gases and 1 molar concentration for all aqueous species. But as we know, changing the concentrations of things can shift reactions forward or backward. That's what Le Chatelier's principle says, and that's because under new concentrations you will have new values for delta H and delta S. Okay, we've been perhaps a little bit careless about this knot here. Remember that technically that means standard conditions. That means 1 atmosphere of pressure for gases and 1 mole per liter for aqueous things. It's not the same as standard temperature and pressure. So standard temperature also implies a temperature, and this knot here, standard conditions, actually can apply at any temperature. It's all about concentrations. This is actually the right place in the textbook to draw attention to that and to define standard conditions, but we have seen these delta, pardon me, delta H naught and delta S naught before. Anyway, so let's leave that equation up there. And let's find delta G naught for the following reaction: to H2 gas plus O2 gas. Where am I? Goes to 2H2O gas at 298 Kelvin at room temperature. Can we find delta G naught? Well, we can look in our appendix A2, and first of all, there is a column in appendix A2 for delta G naught. But I want to make a point that that column only applies for 25 degrees Celsius. Now here we actually do have 298 Kelvin is 25 degrees Celsius, and so we could go ahead and use that column. But I want you to be in the habit of instead calculating delta H naught and delta S naught independently, and then using this equation to calculate delta G naught. Now, delta H naught and delta S naught do technically change with temperature, but those changes are small. Delta G changes a ton with temperature, and so if we use our delta H naught and delta S naught values from 298 K, then we should be able to use them in this equation even if the temperature is not 298 K, and our errors will be modest to small. So that's what we're going to do, and when you look up the, well, I'll just give you this, delta G naught. If you do use that table, Going to be just like the others. We'll sum over the products, and we'll have the stoichiometric coefficient times the Gibbs energy of formation for the products, and we'll subtract from that the sum over reactants, and we'll have the stoichiometric coefficient times the Gibbs energy of formation for those reactants. Okay, just like you calculate delta H's and delta S's. Okay, we don't want to do that this time. We're going to actually look up the delta H of formation and the standard molar entropies for all of these species. And when you do, you'll end up with a delta H naught of reaction for this equal to negative 483.6 kilojoules per mole, and a delta S naught of reaction equal to a negative 89.0 joules per mole Kelvin. And before we just naively plug these numbers into our equation, we should notice the killi that is present for the delta H and not for the delta S. Typically your delta G's will be expressed in kilojoules per mole, so what I really want to do is convert this into kilojoules per mole Kelvin. Okay, so that's going to be negative 0.0890 kilojoules per mole Kelvin. I just divide it by 1,000, and now our units are consistent and we can plug them in here. And I can say delta G naught is equal to delta H naught. That's negative 483.6 kilojoules per mole. Minus the temperature must be in Kelvin. If you're given degrees Celsius, this is one of the times that you must convert it. So minus 298 Kelvin times the negative 0.0890 kilojoules per mole Kelvin. Let's see, and I do not have that answer ready in my notes, so we get to solve it together. Okay, so we have a negative 483.6 times, oops, that's not true, minus 298 times a negative 0.0890. And what I get is negative 457. Kilojoules per mole. Negative 457 kilojoules per mole. So what does that mean? The first thing that we can say about this is that because the delta G naught value is negative, this process is spontaneous at room temperature. Now hydrogen gas and oxygen gas are going to need a spark in order to overcome the activation energy barrier and combust. If you have a balloon full of hydrogen, it's not going to ignite all on its own. However, that's a matter of kinetics. That's a matter of just having enough activation energy. As far as whether it will proceed, all we care about is the delta G naught. So if there is a sufficient activation energy, or if you're sufficiently patient to wait for that activation energy to arise through random thermal fluctuations, then this will proceed. That value, negative 457 kilojoules per mole, is actually quite a large negative value, and so this is a very spontaneous process. But delta G can actually mean something else as well. We do call it a Gibbs energy after all. So, and this is in units of energy. So what does that mean? Does that mean that we're going to get 457 kilojoules of heat energy released in this combustion reaction? Well, no, that's what delta H means. Delta H means the amount of heat that will be released through this reaction. So Gibbs energy is a little bit more abstract. What it means is how much useful work can be extracted from this chemical reaction in a perfectly efficient system. And so if I wanted to use this hydrogen combustion reaction to propel my car forward, I actually would not be able to get 483.6 kilojoules of mechanical energy out of this reaction for every 1 mole of hydrogen gas. That will not work. I'll get 483.6 kilojoules of heat energy, and then I could use that heat energy through a heat engine to get some mechanical work done. And that's how internal combustion engines work, and the efficiency of a heat engine is going to be terrible. And so for 1 mole of hydrogen gas, if I'm relying only on the heat, then you can count on getting like, I don't know, less than 100 kilojoules of mechanical energy out of the reaction. Gibbs energy says, well, if you, instead of extracting the heat and using it in an inefficient heat engine, what if I used it in something like a fuel cell? If I have a hydrogen fuel cell, efficiencies can approach much closer to 100%. And let's just assume that I have some alien technology fuel cell that actually is 100% efficient. Well, then Gibbs energy tells you exactly how much energy you'll be able to get out of that reaction. It is only 457 kilojoules per mole, which is less than the heat released. Okay, so Gibbs energy is an energy in that sense. And it's kind of hard to sort of understand why it is this value, especially if you haven't studied how the physics side of this, like efficiency of heat engines, and we haven't talked yet about electrochemistry and things like that. But anyway, that's why Gibbs energy is called an energy. That's how much energy you can extract. And in this case, it's not a matter of engineering limitations. The best, most perfect engine that you could construct will still have a limit, and Gibbs energy is that physical limit. Okay, well, there we are. Gibbs energy of this reaction at 298 K. Well, what if we take that same reaction and we do it at 5,500 Kelvin? So because we've gone this route and found delta H naught and delta S naught, we can just plug these values in. Delta G naught is equal to negative 483.6 kilojoules per mole minus, and now we'll use our higher temperature of 5,500 Kelvin times where are we? 0.0890 kilojoules per mole Kelvin, and that is a negative as well. Right, so the negative 5,500 times the negative 0.0890. And let's figure out what we get there. You can actually just use my same formula here. I'll just back up here and do 5,500. And this time we get 5.90. Sorry, that looks terrible because I was using a tiny nub of chalk. But we get a positive 5.90 kilojoules per mole. And what this means is that at that elevated temperature, the reaction here is not spontaneous anymore. You might think that a higher temperature, of course, the hydrogen's going to burn, but that's just because you're thinking in terms of activation energy, not in terms of thermodynamics. And in fact, if you get the temperature high enough, hydrogen gas will no longer burn. It's no longer flammable. And this right here tells you that the amount of energy that you can extract is none. It's negative 5.9. You could think of that as meaning that you would have to input 5.9 kilojoules of energy somehow in some coupled reaction in order to drive this reaction forward at that temperature if you wanted to. And again, it has nothing to do with delta H. Combustion of hydrogen still releases heat no matter what temperature you're at. But are you able to extract energy from it? Apparently not at 5,500 Kelvin. And so if we look at this, you know what, yeah, okay. If you look at this, an endothermic reaction that has a positive delta H is going to sort of tend toward having a non-spontaneous delta G naught unless this term is overcome by the second term. And so for an endothermic process to ever be spontaneous at all, it'll need to have a positive delta S naught, and it will need to be run at a sufficiently high temperature. And I don't want to get into more detail about that because that's the whole focus of the next section of this textbook. I just will mention that solvation reactions are a prominent example like this. So for sparingly soluble salts, usually the enthalpy of solvation is endothermic, and that's what makes them sparingly soluble. And how do you get salts to dissolve more than they normally do? Increase the temperature. And of course, going from a regularly ordered crystalline solid to the solvated ions is going to be a positive delta S. So that's just a good example of that. Okay, and that's it for 18.4.